In this video, we will discuss how one can define one-forms and higher-rank tensors on a manifold. We will start with one-forms and show that they define the vector space, which is dual to the tangent space and will be called the cotangent space at a point of the manifold. A special one-form is the gradient of a function, and we will also show how we can do component transformations under a change of basis. Generalizing this to high-rank tensors, we will show how those tensors can be defined as linear maps on vectors and one-forms and form a vector space. And we will also present some of elementary operations on tensors like the tensor product, the contraction, and symmetrization of tensors. So let's start with one-forms. We will assume that we have already constructed the tangent space at the point P of a manifold. Then, one-forms at that point are defined as linear maps on this vector space that take any vector in that space and giving us a real number. This map is assumed to be linear, so for any vectors v and w, any linear combination of those will be mapped to the same linear combination of their images under omega. The one-forms form a vector space by themselves. This will be called the cotangent space, and we will show that this space can be thought of as being dual to the tangent space at the point P. The tangent space is formed under the operations of adding one-forms and multiply them by real numbers according to this equation shown here. And we will also show and construct bases on this tangent space. Let's consider the tangent space first of all. And let's say that it is described by a basis of vectors EA. Then we can construct the basis in the cotangent space, which we will also call EA, but by placing the indices upstairs instead of downstairs, as being the one-forms that map elements of this basis to the delta Kronecker here. This looks like an orthonormal condition between the two bases, but remember that we don't have a structure like an inner product built in to those spaces. The fact that they are one-forms can be seen that when they act on any vector chosen from the tangent space, then the result is to give us a specific result, which is the component of the vector v in the dual basis. So let's consider the components of the vector v given by the linear combination of v in the basis EA. Then the action of EA on the vector v is equal to the action on this linear combination of vectors. So the VBs here are real numbers, the EBs are vectors, and these are sums of their product. EA, being in one form, is a linear map. Therefore, all the real numbers can be taken off the arguments. And what we obtain here is a linear combination of the actions of the dual basis on the original basis, which has been defined to be this delta Kronecker. So when we perform this sum here, the delta Kroneckers give non-zero contributions only when the index of VB is equal to A. So we obtain VA. So since we know the action of EA on any vector V, then we have chosen a one form from the cotangent space. Any one form can be written as a linear combination of those chosen vectors. And the coefficients here, which will be called the components of omega in that basis, are equal to the action of omega on the dual basis EA. Indeed, if we assume this expansion here, then when omega acts on EA, because of the definition of EB being the dual of EA, we obtain here this delta Kronecker, which will select the A component of the one form omega. Therefore, EA upstairs form a basis of one forms, and there are n of them. Therefore, the dimensionality of the cotangent space is equal to the dimensionality of the manifold M. The same thing is true also for the tangent space, as we have already seen. The image of a vector V under omega is called the contraction of omega in V. Let's compute this one, and let's substitute for the vector V here its expression as a linear combination with respect to a chosen basis EB. Because of the linearity of the map, VB can be factored out, and because omega is this linear combination of one forms, then we obtain the action of a member of the dual basis on a member of the vector basis here. That will give us, by assumption, the delta Kronecker here, and the terms that will give a non-vanishing contribution will be the ones where the index A is equal to the index B. So the final result is the sum of those products where the component of omega is multiplied by the respective component of the vector V. So this gives us the contraction of omega in V. Notice the placement of the indices. You will see that in tensor equations, whenever we sum over indices, we sum over an index that is downstairs and an index which is upstairs. The vector spaces, tangent space and cotangent space, are dual to each other. We can define linear maps on one forms that take us from one forms to real numbers. And if we take the linear map V acting on omega, if we define this to be the action of omega on the vector V, then this linear map is indistinguishable from the original vector V. So we can identify the vector V in the tangent space of M at the point P, and a linear map V on the cotangent space of M. So with this operation, we go by duality from the tangent space to the cotangent space, and by dualizing, we go back to the original tangent space. That shows us also that the choice of fundamental objects is not so important. We have chosen to define vectors as the fundamental geometric objects in a previous lecture, and now we build one forms and later also tensors on those objects. But it can be shown in mathematics that we can define one forms to be the fundamental objects and then build vectors as linear functions on those one forms. Given a smooth function on M, a special one form that is associated with a function is the gradient of f. Let's see how this is defined. A one form is defined by its action on any vector v. So we define this one form when it acts on the vector v to give us a number which is the same as the action of v on the function f, which we know that this is the directional derivative of f along a curve that defines v. This is a one form because it is a linear mapping of vectors. If we consider any two vectors v and w, and the action of the gradient on any linear combination formed with those two, then by definition, the result will be the linear combination of the vectors acting on the function f. But this is a linear operation that gives us the linear combination of the action of v on f and w on f separately. But the action of v on f is by definition the action of the gradient on v, and w on f is the action of the gradient on w. So you see that this is indeed a linear map on vectors. If we choose a coordinate system and consider the coordinate basis that derives from it, d mu, then we can compute the action of the gradient on f of f on one of those vectors in the basis. So by definition, this is the action of d mu on f, which we have already computed in the previous lecture to be given by the partial derivative of f with respect to x mu. This is consistent with the definition of the action on any vector v, because here we can substitute for v its expression as a linear combination in the basis d mu, and because this is a linear operation, then this is given by the action of df on each vector d mu separately. But this is the partial derivative of mu with respect of f with respect to x mu, and you remember that this expression here is equal to the action of v on f. For the particular choice of f being the coordinate functions x mu, we can repeat the same process. The gradient of one of those, let's say x mu, on any vector of the coordinate basis d mu is given by the partial derivative of x mu with respect to x nu. But this is the Kronecker delta shown here. So we see that dx mu forms a basis which is dual to the coordinate basis d mu. We will also call this a coordinate basis, of course a basis in the cotangent space. Then, this is a basis because any one form can be written as a linear combination of those one forms, this way. Indeed, the action of omega on d mu can be computed from the right hand side by dx nu acting on d mu. This is the delta Kronecker here, therefore the result is to obtain the mu component of the one form omega. Then omega acting on v is the same as this right hand side of this equation acting on v. We substitute for v its expression in terms of the basis d mu. Because of linearity, we have the action of dx nu on d mu, giving us the delta Kroneckers here, and the final result is the contraction of omega with v. Therefore, the left-hand side omega of v, which we know that it is equal to omega mu v mu, is equal to the right-hand side, which is the right-hand side of this equation acting on v. And since this is true for any vector v, then the one form omega is equal to the one form written on the right-hand side. So this equation here is valid, where omega mu is nothing but the image of d mu under omega. So omega mu is the component of omega in the basis dx mu. If we change coordinates from x mu to x mu prime, then we can consider the gradients of those new coordinates, dx mu prime. Their action on the coordinate basis of x mu is simply the partial derivatives of x mu prime with respect to x nu, and that is coming from the definition of the gradient. But since dx nu is a basis, dx mu prime can be expressed as a linear combination of the dx nu. And this equation here shows us that the coefficients in the linear combination is the right-hand side of this equation. So dx mu prime is obtained by a linear action of the transformation given by the partial derivatives of x mu prime by x nu. And this can be seen as a linear action because if we arrange this in a matrix, we have a matrix here multiplying a column vector dx nu. So if we consider a one-form sigma, we can write down a linear combination with respect to the choice of any basis. Here, dx mu and dx mu prime. And the corresponding coefficients here will be the components sigma mu and sigma mu prime. If we substitute dx mu prime from this expression here, and that gives us the transformation from dx nu to dx mu prime, then we obtain the right-hand side of this equation, and we see that those terms here can be identified with the component of sigma in the dx mu basis, because they're common factors to the dx mu. The dx mu as bases are linear independent, so in any linear combination, the coefficients must be equal. Therefore, the components of sigma in the x mu coordinate system are related to the components of sigma in the x mu prime coordinate system with this relation here. Compare this with the coordinate transformations and their action on the components of vectors. So this was the result that we had obtained in a previous lecture, and you see that there are similarities and differences. You see that the components transform in a similar way by the action of derivatives of components in one coordinate system with respect to each other, to the other, but you see here that we use the inverse of those matrices in these two different cases. That is easy to remember by comparing how indices are placed on both sides of the equation. You see here that downstairs indices are matched with downstairs indices on the right-hand side, and upstairs and downstairs indices are summed over on the right-hand side. And similar here, upstairs index here is matched with upstairs index here, and the rest of upstairs and downstairs indices are summed over on the right hand side. Inverting this relation, we can obtain the components of sigma in the x mu prime coordinate system in terms of sigma mu. For that, we have to use the inverse of the linear transformation, the first equation here, and that is given by the inverse matrix of the derivatives, x mu prime with respect to x mu, which is given now by the matrix obtained by the derivatives of x mu with respect to x mu prime. Let's now try to obtain a pictorial representation of the gradient that will give us some intuition and a geometric picture that we can have in our minds when we think of the gradient, and in fact for any one form. So the gradient is associated with a chosen smooth function on M. And let's consider in the manifold M submanifolds where this function f takes a constant value. So this will form hypersurfaces in the manifold where on each hypersurface the function f takes the same value. In this cartoon we say that f is equal to some value f1, here it is equal to some value f2, and etc., etc. Then if we consider vectors, then the curves that define them will cross those surfaces and pierce them at specific points in most of the time. Let's consider a vector v, which is defined to be tangent on some curve gamma v. So the parameter of that curve is t, and as we move and change t, we move along those points in the manifold, and we cross those three surfaces that are drawn in the cartoon. Then, as we cross each surface, at the respective points of the curve, the function changes its value. So, when it crosses a point on the f equal f3 value, the value of that function changes to f3, whereas when it crosses the f equal f1, the value of the function on that curve is equal to f1. So as we move along t, the observer that moves along that line observes that function to change its value as t is changed. So if we change the parameter on the curve by delta t, then the value of the function is approximately changing by v of f times delta t, and that is because v on f is nothing but the directional derivative df by dt. And when this is multiplied by delta t, it gives us to first order the change of the value of the function. And that will be true for any vector. If we take a different vector w, which is now defined by the curve gamma w with parameter lambda, then we can find the point that it crosses the f equal f3 surface after moving, let's say, after we change the parameter lambda by delta lambda, and then the change of the function will be the same because it will be crossing the same surface at a different point, but the function will have the same value on that surface. So again, this change of the function, which is the same as this one, will be given by the action of w on the function f. So for any vector, this change of the function along the curves is the action of the vector on the function, but this has been defined to be the action of the gradient on the vector. So this v times delta t becomes df times delta t. Now, the gradient is given by the sum of the partial derivatives of f with respect to x mu times the components of the mu, which are nothing but the rate of change of the components dx mu along the curve. So this is approximately equal to the partial derivatives of f with respect to x mu multiplied by the amount that the coordinates have changed by this motion along the curve gamma v. So you see that in this expression there's no reference to the particular vector v anymore. This equation will be true for any vector v, w, u, whatever you like. So the picture that we obtain is that the value of f acting on v is proportional to the number of the surfaces that are pierced by v per unit parameter. We can draw pictures of one-forms in a similar way for any one-form omega. Let's picture omega as a set of parallel hyperplanes in the cotangent space. Then, the action of omega on v can be thought of as being given by drawing an arrow for the vector v and counting the number of surfaces that it crosses. This can be done for any vector v and w, and define each time this contraction. So the denser those hyperplanes are, the larger the value of omega of v will become. So the magnitude of omega will correspond to the density that we draw those hyperplanes. Of course, we have to continue that infinitely so that the piercing for any vector v and w can be defined. So the density of those planes is what gives us the magnitude of omega. We notice that this picture is consistent with the fact that if the action of omega on two different vectors is the same, then those vectors will differ by a vector which is, let's call it parallel to those hyperplanes, with parallel meaning that it does not pierce them anymore, which actually means that the image of this vector with omega is just 0. Then this picture here is consistent with the linearity of the action of omega on vectors. So if you consider the action of omega on a multiple of the vector v, it is obvious that alpha v will pierce alpha times the number of hyperplanes that v does. So this will be alpha times omega v. And in this little cartoon here, you see that the action of omega on v and w will also be equal to the sum of the actions on the two vectors, because if you count the number of hyperplanes that v crosses and the number of hyperplanes that w crosses, then v and w will cross the sum of those piercings. Having defined one-forms at an arbitrary point P of a manifold, we can move on to define one-form fields. So if we assign a one-form at each point of the manifold in a smooth way, this defines a one-form field on the manifold. So being smooth, we mean that if omega acts on a smooth vector field, which is defined because v has a value at every point, so we can compute the action of the one form at that point on the vector at that point, that will give us a number at every point, which is a function on M. And if that function is smooth, then omega is also called the smooth one-form field. If we have a smooth function f, then its gradient at each point forms a smooth one-form field. And the action of that one-form field on a vector field V, it will be given by this formula here. In the special case of coordinate functions, if we consider a coordinate system of the manifold x mu, then the gradient of the coordinate functions form one-form fields that are smooth and cover the chart. And then we can express any one-form field as a linear combination of these one-form fields, and the components omega mu are now smooth functions on the manifold M. A specific example of how a one-form field acts on vector fields, let's take something that is defined only for vector fields, like the Lie bracket of two vector fields V and W. So this is a vector field, and its action and the action of omega on it will be given, will be equal to the action on this vector field here, which is a linear combination with respect to the coordinate basis d mu, given by the components of the Lie bracket in that coordinate system. Omega is linear, is acting linearly on vector fields, therefore this function here can be moved outside the arguments of the map omega. But now we know that when omega acts on a coordinate basis vector, it gives us the component of omega. And we have already computed the components of the Lie bracket, which is given by this expression here. So the contraction of omega with the Lie bracket of two vector fields can be expressed in terms of their respective components by this relation here. So let's move now to higher rank tensors. Tensors are defined to be linear functions on one-forms and vector fields. And if we take such a linear map on k one-forms and L vectors, that defines a tensor of the type k, L. So such a tensor is a linear map on this vector space here, which consists of the product of k times the cotangent space that we make for the first k slots for the one-forms, and L times the tangent space, which will provide L slots for vectors. So these tuples here of one-forms and vector fields must be mapped to the real numbers in a linear way. So the type of a tensor, represented by those two integers k and L, is also called the order of the tensor or the rank of the tensor, and in the bibliography can be found to be expressed with different names like valence and degree. The space of all tensors of a given type form a vector space, which is denoted by T of M with here upstairs pair of indices k and L, distinguishing vector spaces corresponding to different types of tensors. A special case is the case where k is equal to 1 and L equal to 0, which gives us 1, 0 tensors. So this space here can be identified with the tangent space. So any 1, 0 tensor is a vector. Similarly, any one form are tensors of type 0, 1. Let's see all this with some specific examples. Let's consider the simple case of a 1, 1 tensor. According to what we have said, a 1, 1 tensor is a linear map from the product of cotangent and tangent space into the real numbers, such that it takes pairs consisting of a one form and a vector, and giving us real numbers, which we will denote by t on omega and v. So we see t as a map has two slots here, one slot for a one form and one slot here for a vector. The linearity of this map is defined by those two relations here. So when on the first slot we put the linear combination of any two one forms, omega and sigma, the right-hand side should be a linear combination of the actions of t on omega and sigma separately. And it should be linear with respect to the second slot. So when t is acting on a linear combination of any two vectors v and w, then the result should be the linear combination of the separate actions of t on v and w. So let's compute the action of such a tensor on any one form and vector v. We will start by considering coordinate bases, d mu on the tangent space and dx mu on the cotangent space. Then omega and v can be expressed as linear combinations in the respective bases, which are giving us the components omega mu and v nu. The fact that this map is linear means that all the constants, omega mu and v nu, can be moved outside of the arguments of the function. So what we're left over here are the actions of t on elements of the two bases, and considering all possible pairs, dx mu and d nu. Now we call the action of t on the elements of the bases the components of t denoted by t upstairs mu and t downstairs nu, so that upstairs and downstairs match the two sides of this equation. The fact that we call these components of t will be explained later when we choose a basis in the vector space of 1, 1 tensors. So this definition can be extended to any KL tensor if we consider the images of a coordinate basis under a KL tensor, which means putting mu k elements from the dual basis dx mu and L elements from the basis d nu, then any combination of those choices will give us the respective component of the tensor t, which we now see has k indices upstairs corresponding to the first slots and L indices downstairs corresponding to those slots. Then the action of this tensor on any set of one forms and set of vectors here will be given as a linear combination of the components of the respective one forms and vectors and the components of the tensor defined by this relation. So let's move on and see how we can define a binary operation on tensors that can be used to construct higher order tensors. So let's start by considering two tensors, S and T, the first one being of type K1, L1, and the second one being of type K2, L2. Then the tensor product of S and T will be a tensor that is of order which is the sum of the orders of the two tensors. So it will be a tensor of type K1 plus K2, L1 plus L2. And this tensor will be defined by its action on K1 plus K2 one forms and L1 plus L2 vectors. So if we take any such group of one forms and vectors, then the action of the tensor product on them will be given by the separate action, by the product of the separate actions of S and T on the respective one forms and vectors. So here we have K1 one forms that will be put on the first term here, and L1 vectors that will be put here. For the term involving the tensor T, we take the next K2 one forms and we put them on the first slots of the tensor T, and L2 vectors from here and put them in the slots of T here. Notice that this binary operation is not commutative, and the tensor product of S with T is different from the tensor product of T with S. Of course, we have to show that the tensor product is indeed a tensor, so it must be a linear function of its arguments. Of course, this is true, and you can easily prove it yourselves by considering examples of low-rank tensors. We can also show that the components of the tensor product of two tensors is equal to the product of the components of the tensors S and T. We all have to match the indices of the components on the right-hand side with the components on the left-hand side. So you see U1 through UK1 correspond to the indices, to the upstairs indices of the tensor S, and U1 through UK2 correspond to the upstairs indices of the tensor T. And similarly, the downstairs indices lambda 1 through lambda L1 correspond to the downstairs indices of the tensor S, and the downstairs indices rho 1 through rho L2 of the tensor product correspond to the lower indices of the tensor T. So that is a very simple operation obtained by taking simple products of components between two tensors. So let's see the tensor product using special simple examples and start with two one-forms omega and sigma. By definition, the tensor product of omega with sigma acts on two vectors v and w, since this is a 0,2 tensor. Then this action is given by the product of the separate actions of omega on the first slot v and sigma on the second slot w. But we know what those actions are, and because we know the forms omega and sigma. As a special case, consider the elements of a coordinate basis, d mu and d nu, where d mu takes the slot of v and d nu takes the slot of w. So you see that when the tensor product acts on those two coordinate vectors here, we just obtain the product of the two respective components, omega mu and sigma nu. And that means that we can write the tensor product as a linear combination of the tensor product of the dual basis, dx mu times dx nu. So let's see why this is true. So if we take this equation that we want to prove and see how the 0-2 tensors on the left-hand side and the 0-2 tensor on the right-hand side act on the pair d mu d nu, the right-hand side can be computed by considering the action now of the dual basis dx lambda and dx rho on the respective vectors d mu and d nu. Because of the duality of the two bases, the result is that those two delta Kroneckers, delta lambda mu and delta rho nu. But those delta Kroneckers, we select only those terms where the lambda index here is equal to mu and the rho index here is equal to nu. So that will be the product omega mu times sigma nu. But we already know that this is equal to the left-hand side. So the left-hand side can be identified with the 0-2 tensor on the right-hand side. So let's see what this 0-2 tensor gives us when it acts on any vector v and w. So that will define uniquely a 0-2 tensor on the corresponding vector space. So when the tensor product acts on the vectors v and w, it will give us those two products of each one form acting on the respective vectors found in the slots here. But the action of the gradient of a coordinate function on v is nothing but v acting on the coordinate function. That is the definition of the gradient. And we know that when v acts on a coordinate function, it gives us back the component of that vector in that coordinate system. And similarly happens with the vector w here. So if we regroup the factors in each of the terms in the sum of the right-hand side, we have those two factors here where we have here the contraction of omega with v and sigma with w separately. So these are the two contractions. But then we can use the definition of the tensor product, and this product here of the contractions is nothing but the action of the tensor product of omega with sigma on the vectors v and w. So since this is true for an arbitrary pair of vectors v and w, then the 0-2 tensor underlined here is equal to the 0-2 tensor underlined there. The linearity of a tensor product can be seen in this special case very easily. So if we take how the tensor product of omega with sigma acts on a linear combination here of those vectors v and u, alpha and beta being real numbers, then by the definition of the tensor product, this is omega acting on the first slot and sigma acting on the second slot and forming the respective contractions. But omega being linear, this action here is given by the linear combination of the separate actions of omega on V and U respectively. So if we expand this and do trivial algebra, then we have the contraction of omega of V times the contraction of sigma with W, and omega and U times the contraction of sigma and W there. But the product of those contractions is the action of the tensor product on V and W and omega and sigma on U and W. So linearity has been proven. Now we have seen that the set of 0, 2 tensors formed by the tensor product of the dual basis dx mu times dx nu for any pair mu and nu gives us n square 0, 2 tensors that form a basis in the corresponding vector space. We call this a coordinate basis in this vector space because this derives from the coordinates x mu. Therefore, this means, of course, that the dimension of this vector space is equal to the number of the elements in the basis, which is equal to n squared. Let's see why this is true. Let's now take any tensor S and show that it can be expressed as a linear combination of the elements of this basis. First, let's notice that when S acts on the basis d mu d nu, then the result is the component S mu nu. And you can see this is true because if we substitute the right-hand side, then its gradient here acts on the vectors d mu and d nu. These are dual bases. We have the delta Kroneckers here, which gives us non-zero contributions when lambda is equal to mu and rho is equal to nu. So now if we compute the action of S on any vectors v and w, and we substitute their expression in terms of the basis d mu, then because of the linear action of S on vectors, then this is given in terms of the action of S on the elements of the base d mu and d nu. But these are nothing but the components of S mu nu, which has been computed in the previous line. Then let's take the right-hand side and act on any vector v and w. Then, as before, this is given by the product of the actions of the dual basis on v and w. And by the definition of the gradient, this is just the action of v on x mu and w on x nu, which gives us the components v mu and w nu. So the right-hand sides match for any vector v and w. Therefore, the 0, 2 tensor S must be equal to the 0, 2 tensor given by this linear combination of 0, 2 tensors. So we have proven that indeed S can be written as a linear combination of those 0, 2 tensors formed by the tensor product of dx mu and dx nu for any pair mu and nu. So let's see what happens when we change coordinates. When we change coordinates, the dual basis on the cotangent space also changes. And you remember this transformation rule that gives us dx mu prime in terms of dx mu, the coefficients being here the derivatives of x mu prime with respect to x mu. So that will give us a new basis in terms of dx mu prime and dx nu prime, and we can express the same tensor S as a linear combination on those two different bases. And the coefficients here will define the components of S with respect to those two different bases. Now, in this linear combination, we can substitute what we have found for dx mu prime. So we have this for dx mu prime and this for dx nu prime that has linear combinations in terms of dx mu and dx nu. So linearity again comes into play, and we can factor out all the numbers here in the parentheses, and this is a 0-2 tensor dx mu times dx nu. So if we compare those two expressions, because those vectors in the vector space of 0-2 tensors are linearly independent, then those two terms must be equal. So we have a relation between the components of S in these bases and the components of S in that basis. So this is a linear operation given again by the matrix of derivatives of x mu prime with respect to x mu. And if we invert this relation, we can have the coordinates of S in the prime coordinate system in terms of the coordinates of S in the original system, also given by the inverse derivatives here of x mu with respect to x mu prime. Similar relations we can have between components of tensors by a change of basis, by the change of any basis in the vector space of 0-2 tensors. So let's start with an arbitrary basis in the cotangent space and its dual basis in the tangent space, so that when these one forms act on those vectors, the result is given by Kronecker delta. And we have seen that this defines one forms that are a basis in the cotangent space. And we call this basis the dual of that one. So then S can be expressed as a linear combination of the tensor product of any two pairs of the basis EA in the cotangent space. And those real numbers here are called the components of S in this basis, and they are equal to the action of the 0-2 tensor on the vectors that belong to the basis in the tangent space. Indeed, if we consider S acting on EA and EB, then this will be the same as this 0-2 tensor acting on EA and EB. Because of the definition of the tensor product, each term here is given by the separate actions of a vector in the dual basis on a vector here, and a vector on the dual basis here on the vector EB here. Because of this being defined as the dual basis of this one, the result here are delta Kroneckers that will give us non-zero contributions only when the C index here is equal to A and the D index is equal here to B, is equal to B. So indeed, the action of S on EA and B will give us the component SAB of the tensor in the basis EA times EB. Now, let's see now an example of a higher rank tensor and consider T to be a 2-1 tensor. T being a 2-1 tensor, it means that it acts on 2 1 forms and one vector and gives us a real number. So there are 3 slots for this tensor here, 2 of them to be filled with 1 forms and 1 here to be filled by a vector. The components of that tensor in a coordinate system is given by the action of the tensor on the corresponding dual basis and the basis d rho. And having those components, we can find a basis in this vector space consisting of tensor products of 2 coordinate vectors and 1 gradient dx rho here. If we choose a basis that is not a coordinate basis, then we can express it as a linear combination of taking here 2 elements of the basis EA, these are vectors, and 1 element from the dual basis, which is 1 form. If we make a change of coordinates, then the gradients dx mu transform to dx mu prime, and the vectors d mu transform to d mu prime. Then a tensor, the tensor T is a linear combination of the basis formed by the tensor product of 2 coordinate vectors and one form. So if we express each coordinate vector as a linear combination of the coordinate vectors d mu, and here d nu prime in terms of d nu, and similarly we do that for the dual basis, and we express the 1 form gradient dx rho prime in terms of dx rho, we can factor out all those numbers in these parentheses, and we see that this is simply the coefficient of a linear combination in the basis formed by the coordinate vectors and 1 forms in the x mu coordinate system. So this is nothing but the component of T in the x mu coordinate system, and we see that this is equal to this number here. Notice the placement of the indices here. So we have 3 indices, mi, ni, and rho, which are to be found on the same floor, mi, ni being upstairs and rho being downstairs. And all the indices here are contracted with corresponding indices of the derivatives here. So you see this is also a linear operation on components that gives us the components on a new coordinate system. Now let's consider 2 tensors of different rank. A tensor T is of the 2-1 type, and a tensor R is of the 1-1 type. Therefore, T has components T upstairs mi ni downstairs rho, and can be written as a linear combination in this basis here in a coordinate system. D mu and d nu are vectors. Dx rho is a 1 form corresponding to the rank of the tensor. And this is a 1-1 tensor, so its components is lambda upstairs, sigma downstairs, and the basis here is formed by the tensor product of vector d lambda with the one form dx sigma. Let's compute now the tensor product of those two tensors. Since this is a 2-1 tensor and this is a 1-1 tensor, their tensor product will be a 3-2 tensor. And as such, it will be a linear map on 3 one forms and 2 vectors. And we have seen that this is defined by the product of the actions of t and ρ with the respective one forms and vectors. So we can take the tensor product by considering the tensor product of those linear combinations that give us the two tensors. So what we will obtain is the product of the two components of the respective tensors. And here you see we have d mu dx rho from the first term, d lambda dx sigma from the second term. Now you see this is not politically correct because we mix vectors and one forms in a way that does not conform with the formal definition. So in the formal definition, we usually move the one forms to the first slots and the vectors to the last slots. But this is no problem. This is not a real problem because when we write such an expression, we actually change the order of the slots. So if we write the tensor product of t and ρ in this form, we actually put omega and sigma in the first slots, then we put the vector v, and then we put the vector ρ after that. And last but not least, we put w in the last slot. If we want to write the politically correct expression, we have to move the three vectors d mu, d nu, and d lambda to the first positions of this tensor product and the one forms to the last ones. But you see, this does not correspond to different tensors because all we have to do when we have a tensor is to know how we map one forms and vectors to real numbers, and this doesn't depend how we move around the slots. We just have to put the correct object to the correct slot. So all it matters here to make those two expressions equivalently is that we contract the indices with the same object. So lambda here is contracted with d lambda here, and lambda here is contracted with d lambda there. And the same way here, since we moved dx rho, so you see rho index here of the t tensor is contracted with dx rho here, and the rho index here is contracted with rho index there. So if we make those contractions correctly, and of course we keep the definition of the components by considering the canonical form, then this tensor and that tensor is the same tensor. So let's now consider contractions, and we will define them by using a simple example. Let's consider again the tensor T, which is a 2-1 tensor with components T, mi, ni, upstairs, rho, downstairs. So this tensor here is given by a linear combination of the corresponding coordinate bases d mu times d nu times dx rho. So define now a tensor of lower rank. Notice here that we have a 2-1 tensor now we will define a tensor that has one rank lower on each of the slots K and L respectively. So this 2 here will become a 1, and this 1 here will become a 0. And the way we make this definition is by filling those last 2 slots by elements of the coordinate basis, dx lambda and d lambda. And then we take the sum of all the terms obtained by putting here the same dx lambda and the same d lambda and summing over all possible values of lambda. You see that the result leaves an empty slot here. So we can fill this with any one form and have a linear function. So this is actually a 1-0 tensor, a vector. So in order to compute this tensor, what we do is we substitute the vector dx lambda to the correct position of the tensor product and d lambda here to dx rho, and we obtain the action of d nu on dx lambda and the action of dx rho on d lambda. Now you see that this is left alone, so d mu here will remain. But d mu, we have to remember, is a vector, whereas those two contractions here are numbers. So that will leave us with something that is a number times a vector. So this is a vector. But those two contractions just gives us those deltas of Kronecker, and in this sum here for given mu will select terms that the new index here is equal to lambda and the rho index here is equal to lambda. So the result here will be a sum where the components are summed over the same indices in this position and that position. So for a fixed mu here, this is something like a trace. But there is a leftover index here, mu, that is contracted with the vector d mu, so this is actually the components of a 1-0 tensor. So this 1-0 tensor, we say that it comes from the contraction of the nu and rho indices. That can be generalized to any tensor of type KL. And when we choose two indices to contract, the result will be a K-1, L-1 type tensor. So this will be a tensor whose components are obtained by summing over a chosen index here, any one that we like to pick, with an index downstairs, which is the one that we have picked from downstairs. So this sum here will give us the components of a tensor that have one index less upstairs and one index less downstairs, a K-1, L-1 type tensor. We can also contract indices between different tensors, and for that we have to use their tensor product. So let's see that with an example. Let's say that T is a 2-1 tensor and R is a 1-1 tensor. Then, as before, we can form their tensor product, which is a 3-2 tensor given by the linear combination in this coordinate basis in the space of 3-2 tensors. So if we make the choice to contract this index of T with that index of R, the result will be a tensor that is of order 2-1. So 3 has been reduced by 1 to 2, and 2 has been reduced by 1 to 1. So since this is a 2-1 tensor, this will have this can be expressed as a linear combination of this basis in the space of 2-1 tensors, and the components of that new tensor, let me call it temporarily by the letter S, will be obtained from the components of T and R when they are summed over by contracting those indices, rho and lambda. So you see we pick up components where this index is the same as that index, and we sum over them. So the interesting thing is that this operation will lead to a new tensor and not to something else. Tensors that have a symmetry under the exchange of vectors and one forms that they take into their slots play an important role in physics. And the symmetry under this exchange corresponds to symmetry under the exchange of indices in their components. So we start by considering symmetric tensors and start with some simple examples, like that of a 0,2 tensor that has components g mu nu. Such a tensor is totally symmetric in each of its two indices if every component g mu nu is symmetric under the exchange of the two components, so g mu nu is equal to g nu nu. This is a geometric concept, doesn't have to do with a particular choice of the coordinate system, because if you remember the mu nu components of this tensor is just the image of those two coordinate vectors, d mu and d nu. So the fact that these two components are equal, it means that the image of d mu and d nu under G is the same as the image of d nu with d mu. And that translates for any vector, prove that, v and w, the image of v and w under such a symmetric tensor is the same as the image of w and v. So, if g nu nu is symmetric under two of its indices, it's also symmetric in any other coordinate system. So, prove this by considering coordinate transformations, and it is very easy to convince yourselves that this is actually true. So we can have symmetric tensors with respect to two of the indices, like here in the case of a 0,3 tensor, and we say that this tensor is symmetric under the exchange of its first two indices if a mu nu rho is equal to a nu nu rho. We can have symmetry under the exchange of more than two indices, like in the case of the tensor A being symmetric under the exchange to any of its three indices. In this case, we have 3 factorial possible arrangements of the indices, so for that to be true, all those components have to be equal to each other. To construct all those combinations is easy in the case of the 3 indices. Simply write the 3 indices, nu, nu, and rho, and visit them in a cyclic way. So here we start with mi, going to ni, then to rho, then we move on to the slot rho, and then go from rho to mi to ni, then we start from ni, and going from ni to rho to mi. And then we do the same thing, but going the other way. So if we start from the position rho here, we move counterclockwise to nu, and then to mi, and form alpha rho nu mi, and then start from mi, going to rho ni, and then start from ni and go to mi and rho. So this way we form all the possible 6 permutations of the 3 indices. We can generalize this to more than 3 indices, but then the work, although not very hard, it's much more tedious. So, after we have defined what symmetric tensors are, we can use this definition to start from a tensor that does not necessarily have the symmetry and form tensors that do have the symmetry. So, for example, we can take the tensor G mu nu, and without assuming that it is symmetric under the exchange of mu and nu, we can form the tensor that has components G mu nu plus G nu mu. That tensor is obviously symmetric under the exchange of mu and nu because all it does is to change the order of this sum. The symmetrization of these two tensors is defined by putting here this normalization factor. And be careful, it's not the same in all textbooks. By putting it here, you see that we kind of define the average of those two components to be the component of the symmetric tensor. We can symmetrize two indices of any tensor by isolating them and do the symmetrization only with respect to those two. So here we perform the same operation, but only by exchanging the first two indices, mu nu, nu mu. Symmetrization can be done for any number of indices, and here we show the example in the case of 3 indices. So here we write all the possible combinations that we formed in the previous slide, and we normalize this to the number of terms in the sum. So there are 3 factorial terms, 6 terms. So we divide this by 3 factorial. And if we generalize this to any number of k indices, and let's say that we perform a full symmetrization of a 0k tensor here, then this is done by taking the average of the sum of components with obtained by all permutation of the mu1 through mu k indices here. So we have k factorial such permutations, and let's remember here what a permutation is formally. It is a one-to-one map from a set of indices to another that gives us the same number of indices here, but the integers here have just been moved around. So that is the one-to-one requirement here for the map. So here the summation over sigma means the summation over all possible permutations of mu1 through mu k. We can also consider tensors that are anti-symmetric under the exchange of 2 or more indices. So, for example, here we see a 2-0 tensor that is antisymmetric under the exchange of its indices mu and nu. And being antisymmetric means that after we perform the permutation of these two indices, we have here a minus sign. And a tensor can be antisymmetric under the exchange of 2 of its indices if when we do the exchange, we obtain the same number with the opposite sign. So if we have a tensor that is antisymmetric with respect to k of its indices, it means that if we perform any permutation of those indices, then the component obtained will be either plus or minus the original one. The plus is obtained if the permutation is even, That means it can be obtained by an even number of elementary permutations of a pair of indices, and minus when the permutation is odd. So this plus and minus is usually denoted by sign of the permutation sigma. So here, when this relation holds, this component here, that is obtained by permutation sigma of the indices here, gives us the sign of sigma, then the tensor S is antisymmetric under the exchange of the indices mu1 through mu k. Similarly to the process of symmetrization, we can define the process of anti-symmetrization. So let's start with the easy stuff. If we have any tensor of type 2,0, we can form a tensor of the same type, which is antisymmetric under the exchange of its indices mu and nu by considering this difference here. So you see that this is antisymmetric under the exchange of mu and nu because the minus sign will be moved on to the first term. And we can antisymmetrize the tensor of any type with respect to two of its indices by forming similar differences, as we do in the case of the 2,0 tensor here. We can antisymmetrize with respect to any number of indices, like the example here shows for 3 indices. Now, in the case of the 3 indices, it is easy to compute the sign of the permutation. So, as in the case of the symmetric tensor, let's write here all possible permutations of mi, ni, and rho by considering cyclic motion along the indices. So a permutation in that case is even when we move clockwise, so all these terms here come with a plus sign, and odd when we move in the counterclockwise direction. So all these terms here come with a minus. If we try to do that for a larger number of indices, the work is much more tedious because not only we have to determine all possible permutations, but we have to determine also the sign of the permutation. So now I will show you how to do that in a following video.